Hello, in this chapter 12, we will be discussing alcohols and phenols. Some of our learning objectives include to describe the structure, properties, and nomenclature of alcohols, discuss their acidity, including three factors that determine relative acidity, discuss the preparation of alcohols by reduction, functional group transformations that can be used to synthesize diols, Grignard reactions, explain how incompatibility between hydroxyl group and a Grignard reagent can be overcome, describe the industrial synthesis of phenols, substitution and elimination reactions of alcohols, the oxidation reactions of alcohols, the functions of NAD+ and NADH in biological systems, to identify and explain the importance of the oxidation product of a phenol, and design a synthesis involving a carbon-carbon bond formation. Let's begin by defining what is an alcohol. We know from our discussion regarding functional groups that alcohols possess an OH or a hydroxyl group. Hydroxyl groups are extremely important in natural compounds, so anything that contains an OH group by itself and then an R group, such as an ethyl group in ethanol, cyclopentyl group in cyclopentanol, these are considered alcohols. Hydroxyl groups in natural compounds, there are many. Here are a few examples. Geranium, for example, is isolated from roses. It's used in perfume. You have it right here. That's OH, tells you that you're dealing with an alcohol. And cholesterol, again the OH, which will tell you that it has that functional group. Phenols possess a hydroxyl group directly attached to a benzene ring. So every time you see benzene and an OH right adjacent to it, then you are dealing with a very specific type of alcohol known as a phenol. Those are also very common in nature. We have two examples here, capsaicin and THC. Now, how do we name them? Alcohols are named using the same procedure we discussed in chapter 4 to name alkanes with minor modifications. First, we identify the parent chain, which should include the carbon that the OH is attached to. Then we identify and name the substituents. After that, we assign a number and, if necessary, a prefix to each substituent. Give the carbon that the OH is attached to the lowest number possible. List the number of substituents before the parent name in alphabetical order. Ignore prefixes except for iso when ordering alphabetically. The hydroxyl number is placed either just before the parent name or just before the OL suffix. Here we have a few examples. We have penthane, so our parent chain would be consisting of 5 carbon atoms. And if we have an OH on either end, then it will be pentan, right? Penthane, pentan, and then OL, all for indicating that we have an alcohol, so pentanol. So in this case, the second case we have here at the bottom, the parent chain will be octane, so 8 carbon atoms. But remember that the parent chain must include that hydroxyl group. So we kind of have to cut this and make it into an hexane. So it will be hexanol. And we start numbering, making sure that the carbon attached to the hydroxyl has the lowest number possible. So 1, 2, 3, 4, 5, 6. Carbon number 2 would have a propyl group. So this will be 2-propyl hexanol. Assign a number, prefix, etc. So here, just like we mentioned before, that OH must have the lowest number possible. The OH number is placed either just before the parent name or just before the OL suffix, just like we saw with alkanes and alkynes. So this can be either 3-pentanol or pentane 3-O, right? Either is accepted, either are correct. For cyclic alcohols, the OH is always carbon number 1. So cyclopentanol, you're not going to see a number because it's always going to be 1. In the case of having other substituents, like in the case here in the top right, we put numbers on everything else, right? Because we assume OH is in the carbon number 1, in which case then the two methyl groups here would be in position 3. So this will be R33, the methyl cyclopentanol. We will also see a bunch of frequently used common names not necessarily attached to IUPAC, such as N-propyl alcohol, isopropanol, terbutyl alcohol, or terbutanol, etc. Just like with halides, alcohols are often classified by the type of carbon they're attached to. In other words, we will see them as primary, secondary, or tertiary alcohols. This is going to be very relevant when we discuss the kinetics and thermodynamics of reactions involving alcohols, just like with alkyl halides. We saw before the phenol group, which is the OH attached to a benzene ring, and when you have other substituents, then you use as the base or the parent name would be phenol, and then we look at everything else. So for instance here, we know that OH is in position 1, I'm sorry, 2, 3, 4. So 2, we have a nitro group. 4, we have a chlorine, so a chloro group. So this will be in alphabetical order. Chloro goes first, so 4 chloro, 2 nitro, and then phenol. Methanol is going to be the simplest alcohol with just one carbon atom. With a suitable catalyst, about 2 billion gallons of methanol are made industrially from carbon dioxide and hydrogen molecules every year. Methanol is poisonous. It actually causes blindness, but it has many uses. It is a solvent, precursor for chemical synthesis, and fuel. It's also paint thinner. And, when you paint with oil-based painting, this is the compound you use for removing and cleaning your tools. Ethanol, E, so that's another carbon atom. It is produced by fermentation of grains and fruits. Industrially, ethanol is made via acid-catalyzed hydration of ethylene. Ethanol has many uses, many of which we may be a little bit more familiarized than others. It is a solvent, it is precursor in chemical synthesis and fuel. It is denatured to avoid heavy taxes. Human consumption, ethanol is suitable for drinking and is heavily taxed. So basically, every time you're using ethanol for spirits, beer, and other alcohol-containing drinks, then we don't call it denatured. When we use it for chemical synthesis, such as in labs and other processes, then we call it denatured. And there's a tax reason for it, basically, is what this says. Isopropanol, this is also known as rubbing alcohol, is made industrially from the acid-catalyzed hydration of propylene. Isopropanol is poisonous, but it has many uses. It's an industrial solvent, it is an antiseptic, and a gasoline additive. The hydroxyl group of an alcohol has a big effect on its physical properties. Let's look at the boiling points below. Ethane has a negative 89 degrees Celsius boiling point. Chloroethane goes all the way up to 12, but then ethanol is 78. The main reason for this, as you may imagine, is going to be the ability to hydrogen bond. That makes a world of difference in terms of boiling points, and it all comes down to intermolecular forces. Alcohols with 3 carbons or less are miscible in water. They're considered polar to an extent. The more carbon atoms you add, then the lower that polarity. When you have 4 and more, then they don't really mix with water really well. They're considered immiscible. But the reality is that there's a gradient, right? So 4 carbon atoms is going to be soluble, but only to an extent. 5 carbon atoms becomes less so, and so forth. Now, when you deal with 6 carbon atoms or more, then you will be able to see those two phases if you try to mix them. The reason is that you have a hydrophilic or a polar region, and then a hydrophobic or a non-polar region. When you have more than 4, 5, 6 carbon atoms, the hydrophobic region becomes significant enough that it tends to predominate, and it prevents a lot of the interactions you would see between water and the molecule, making them immiscible to a very large extent. An alcohol's potency as an antibacterial agent depends on the size of the hydrophobic group. The alcohol needs some water solubility to travel through aqueous media, and to kill a bacterium, the alcohol should have a significant hydrophobic region to penetrate microbial membranes. So when you're dealing with selection of an alcohol for antibacterial purposes, then you have to compromise between the size of that hydrophobic region and the hydrophilicity, or the ability to interact with water. You must have both in order for this process to occur efficiently. Hexyl resorcinol is used as an antibacterial and as an antifungal agent. You can see here, it possesses a really good combination of nonpolar. Right? You have the chain, you have the benzene nonpolar, but then you have two hydroxyl groups. So it complements really well. It combines really well the hydrophobic and the hydrophilic regions of that molecule. Let's talk a little bit about acidity of alcohols and phenols. A strong base is necessary to deprotonate an alcohol. Sodium hydrate is often used to generate the corresponding alkoxide. So the alkoxide is going to be the alcohol without the proton, right, the anion. So in this case, from ethanol, the alkoxide will be ethoxide, right? We talk about ethoxide as this part of the molecule, and then the counter ion will be the sodium, so sodium ethoxide. In which case, then you get hydrogen gas as a side product. Sodium, potassium, or lithium metal is often used as well. So they tend to be used as catalysts or active participants really in this reaction. The alkoxide, by definition, is going to be the conjugate base of the alcohol. And just like we saw on our acids and base chapter, we use the same criteria for determining the relative strength of the acidity of an alcohol. We know that by resonance, a phenol is millions of times more acidic because the conjugate base, that phenoxide, we see it right here on the bottom left, is resonance stabilized. For that negative charge to sort of be placed along the entire molecule, making it a lot more stable than if it couldn't. When we talk about inductive effects, we talk about presence of electron withdrawing groups, and they tend to increase the acidity of an alcohol or a phenol, just like we saw on our chapter 2. Effects of solvent: the more poorly solvated conjugate base, the less stable it is, and the less acidic its conjugated acid. So the conjugate base of terbutanol is less stable due to solvation effects. Keep in mind that this is highly branched, so for solvent molecules to sort of get in there and stabilize, it is very challenging. Therefore, you don't get as much stability through solvation than something straightforward like ethanol, for example. The butoxide ion is sterically hindered and not well solvated, like we just mentioned. Alcohols can be synthesized from alkyl halides via substitution. So literally you just change that halogen for a hydroxyl group, and that's pretty much it. The substitution may happen via SN1 or SN2, and it really depends on the substrate, just like we saw on our nucleophilic substitution discussion. So for a primary alkyl halide, you add your strong base, you add your hydroxyl group, and it happens via SN2, so one step, you get an OH. For tertiary, you have a more stable carbocation intermediate, so you get SN1 mechanism. Alcohols can be synthesized from alkenes via addition reactions, in which case you have a number of mechanisms. It really depends on where you want that hydroxyl group to land. Right? You want a diluted sulfuric acid for your secondary alcohol, or with your reducing agent. You may also try a peroxide route for your terminal alcohol. So as a catalyzed hydration and oxymercuration demercuration will lead you with that secondary, in this case, and hydroboration oxidation will give you that primary hydroxyl, that primary alcohol. Let's remember that as a catalyzed hydration yields a Markovnikov addition, whereas a hydroboration oxidation yields an anti-Markovnikov addition. That's why you get your secondary versus your primary. A third method to prepare alcohols is by the reduction of a carbonyl. So what is a carbonyl? A carbonyl is when we have that carbon-oxygen double bond. And if we can protonate that oxygen and remove that double bond, then we effectively have an alcohol. Remember that reductions, just like we saw in our general chemistry, reductions involve a change in oxidation state. Oxidation state are a method of electron bookkeeping. You don't have actual charges, we just count as if we had, but they really don't. Remember how we use formal charge as a method of electron bookkeeping? So it's very similar. Each atom is assigned half of the electrons it is sharing with another atom. And in the case of methanol, the question is, what is the formal charge, which we'll see in just a second. Here, for instance, the oxidation number of methanol will be -2. Each hydrogen is assigned a +1. The OH, oxygen is -2, hydrogen is +1, so this entire group is going to be -1. The entire molecule is neutral, so for everything to be neutral, carbon must have an oxidation number of -2. When we look at this guy right here, then the oxidation number changes a little bit. Oxygen is a -2, hydrogen is +1, so +1 and +1, -2. That already neutralizes the whole thing. Carbon has an oxidation number of 0. So this is just a way for us to figure out what is the oxidation state, and you can see we can apply that to pretty much every scenario. Oxidation states from carbon will range from -4 all the way to +4. There is not necessarily a preferred number. It really depends on context quite a bit. All of the molecules you see here are very stable, but as you can see, they have very different oxidation states. When we talk about oxidation reactions, we're talking about the carbon's oxidation state being increased, going up, and a reduction is when the oxidation state goes down. So the consequence of the ideas that we just discussed is that when you're converting a carbonyl to an alcohol, you need a reduction process to happen. And for that, you need a reducing agent. The reducing agent is then oxidized in the process, but it precipitates the reduction of somebody else, in this case, the carbonyl bond. The reduction of a carbonyl bond overall results in the addition of two hydrogens across the pi bond that we see here. There are two reducing agents that can be used: sodium borohydride, which is a common reducing agent for aldehydes and ketones. And as you can see, the reaction is actually fairly straightforward. Sodium borohydride, you can see, is very proton rich, so it actually does allow for those hydrogens to be donated to the carbonyl bond to form your alcohol. Sodium borohydride is a source of hydrates, as I just mentioned, which does nucleophilic addition to the carbonyl carbon, followed by a proton transfer from the solvent. This is an important point because one of the protons that you get, you actually need two. One of them gets added from the actual reducing agent, so you have the attack, and then the electron pair moves into that oxygen. But then when that happens, there is a pair of electrons that will attack a proton of this solvent. That's where you get your second proton. So this one comes in from the reducing agent, and then the second one is going to come in from the solvent. When an unsymmetrical ketone is reduced, then a new chiral center is created, and a pair of stereoisomers is obtained as a consequence. So in other words, you get something like this. You have your protic solvent, your reducing agent. You can get one or the other. And if you can get both, then you will get both. The second reducing agent, this one we try to avoid using it in the lab because it's really violent. It's lithium aluminum hydrate. It's another common reducing agent for carbonyl bonds. Lithium aluminum hydrate is often abbreviated as LAH. You will see this throughout the rest of the presentation. You probably see this in your homework as well, so it's important that you familiarize yourself with the abbreviation. Lithium aluminum hydrate and sodium borohydride are structurally similar hydride agents. They both do the same thing, right? They provide that hydrate and then allow for the protic solvent to add that second solvent, the second proton. But lithium aluminum hydrate is much more reactive than sodium borohydride. It cannot be used in the presence of protic solvent. The proton source must be added after the carbonyl is reduced. So in this case, while you still have that two-step process, you're still getting the proton from your solvent, the second proton. You must do that first reduction first. Once you completed that first part, of nucleophilic attack, sort of remove that lithium aluminum hydrate, and then you add your protic solvent. The reactivity of hydride delivery agents can be fine-tuned by using derivatives with varying R or alkyl groups. You use alkoxides, cyano groups, or sterically hindered groups to make things go a little bit slower, a little bit more controlled for us. Lithium aluminum hydride is strong enough to also reduce esters and carboxylic acids, something that sodium borohydride is not able to do. Reduction of carboxylics and esters would yield primary alcohols. Now for the reduction of an ester, you can see an ester right here. For instance, you have an oxygen here, this is going to be reduced. You actually need two equivalents of the hydride. The first two steps result in formation of an aldehyde, which is then reduced to the alcohol as we saw before. So you get this, you have your alkoxide, and then you form an aldehyde. So you get rid of this group right here. And then afterwards, with your second equivalent of lithium aluminum hydride, you form your alcohol. Methoxide is not a good leaving group, but acts like one here because the high energy intermediate becomes a stable aldehyde. Diols is when you have two OH or two alcohols. They can be prepared from the reduction of diketones. So as long as you have the corresponding diketone, you can form your diol however you require. You can do that by using either lithium aluminum hydride or sodium borohydride. Keep in mind that if you're using lithium aluminum hydride, you need to break this down into two steps. Whereas with sodium borohydride, you don't really, you just add everything together and give it some time. Recalling two important reactions from our alkene chemistry chapter, both of these reactions convert an alkene into a vicinal diol, meaning two alcohol groups are added to adjacent carbons. The key difference is not whether we get a diol, but rather the stereochemistry of how those hydroxyl groups are added. In the first reaction, we use catalytic osmium tetraoxide with NMO. This gives a syn dehydroxylation, meaning both hydroxyl groups are added to the same face of the double bond. If one hydroxyl is added above the plane, the other is added above the plane as well. That's why in the product shown here, both hydroxyl groups are represented as wedges. In the second reaction, we first form an epoxide using a peroxy acid and then open that epoxide under acidic conditions. Because epoxide opening occurs through backside attack, the overall result is an anti-dehydroxylation. The two hydroxyl groups end up on opposite faces of the ring, giving a trans diol. Notice that one OH is shown as a wedge and the other as a dash. Now let's talk a little bit about how to prepare alcohols via Grignard reagents. Grignard reagents are often used in the synthesis of alcohols. To form a Grignard reagent, we take an alkyl halide and we treat it with magnesium metal. The electronegativity difference between carbon and magnesium is large enough that the bond has a significant ionic character. The carbon atom behaves like a carbon anion and is a strong nucleophile as well as a strong base. Grignard reagents react just like lithium aluminum hydride and will attack the carbonyl of a ketone or an aldehyde. So the process is actually very similar. The reagent does change a little bit. The key difference is that the Grignard reagent will give you a new carbon-carbon bond. So that's actually interesting because now you can start adding groups via Grignard reagents while at the same time forming your hydroxyl group. Because the Grignard is both a strong base and a strong nucleophile, care must be taken to protect it from exposure to water or alcohols. In the lab, if you're doing Grignard reactions, you actually have to dry everything, oven dry it the day before, and make sure there's very little, if any, humidity when performing Grignard reactions. You can see it reacts readily with water, um, and when that happens, then you no longer have your Grignard reagents. You get anhydrous esters that are usually used as solvents for Grignard reactions. Some examples of Grignard reactions. You can see the addition of that methyl group right here. So basically, the group that you want to add, you started off as an alkyl halide, that alkyl group. You can form your Grignard reagent, and from there you add it through the formation of a hydroxyl bond. Let's look at the reaction below. The alcohol can act as an acid, so Grignard reagents and alcohols are incompatible. the alcohol can be protected to prevent it from reacting. So if you see here, for instance, we have the alkyl, right? The alkyl group, then you have an OH, and you have a halogen, you add the magnesium. So this part is actually a Grignard reagent, but you actually have an OH. This doesn't really happen in real life, but if it did, then this would be your product. So typically what you will need to do is to protect this side of the molecule so that it doesn't interact with the magnesium and with that process of the Grignard reagent formation. So for that, you need a three-step process, which is required to achieve the desired overall synthesis. First, protect the alcohol. Second, perform the Grignard reaction, and then remove the protecting group or deprotect the alcohol. So for you to perform the reaction we just saw, we first take that OH and we add something, usually something bulky like some high liter butyl, phenol groups, big groups that will prevent any interaction from this side of the molecule. Once we do that, then we perform the Grignard reaction just like we saw, and then we exchange this for the proton once again. One such protecting group is trimethylsilyl. So it's a very relatively large group, silicon, and then three methyl groups. We abbreviate that as TMS. So OH, then you form OTMS, then you perform Grignard reaction, then you go back from OTMS to OH. Now for TMS protection, for that step, you need the presence of a base to neutralize the hydrochloric acid byproduct. Evidence suggests that substitution of the silicon atom occurs by an SN2 type mechanism because silicon is much larger than carbon. It's actually under carbon in the periodic table. It is more open to backside attack, which is why we think that it happens through SN2 mechanism. Once you are done with your Grignard reaction, you need to remove the TMS, and that can be done with either hydronium or with fluorides. That will leave you with the corresponding alcohol. TPAF, molecule right here, tetrabutyl ammonium fluoride, is typically used as your fluoride ion supply. The overall process, you start with your alcohol on one side, halogen on the other. First you protect, you add that TMS, and after that then you go ahead and you perform your Grignard, adding whatever R groups you need. Once you're done here, then you remove that TMS, you add that proton once again. That's pretty much it. Phenol is a very important industrial chemical with about 2 million tons produced each year. One of the primary manufacturing routes is the cumene process shown here. First, benzene reacts with propene to form cumene. Cumene is then oxidized with the oxygen to produce cumene hydroperoxide under acidic conditions. Then we get that the hydroperoxide rearranges and cleaves to get two products, phenol and then acetone. One reason this process is so economically attractive is that both products are actually valuable. Phenol is used to make pharmaceuticals, polymers, adhesives, and many other things, while acetone is itself an important industrial solvent and a chemical feedstock. We use this for either as a solvent or starting material for a number of other processes. Now let's talk a little bit about the reactions of alcohols, substitution and elimination. We already know the basis of it, we're just going to be applying it to alcohols. Let's start with tertiary alcohols. They're converted to alkyl halides with a hydrogen halide SN1 type reaction, just like the one we see here. You have your protonation, your OH. OH is a bad leaving group, but H2O is actually a very good leaving group. It leaves, form your stable carbocation, and then you get your halogen. For primary and secondary alcohols, instead of SN1, you get an SN2 type process, so one step concerted. That's pretty much it. To make an alkyl chloride, zinc chloride must be used with hydrochloric acid. The zinc cation is required to make the hydroxyl a better leaving group. So a lot of the reagents that you will see that don't really seem like they belong, usually they're there because they catalyze the process, they facilitate this reaction. In this case, the hydroxyl group is not a very good leaving group. Therefore, you need something to make it easier, either a protonation step or a step just like this one where you're adding that zinc chloride as part of the process. Recall that hydroxyl group can be converted into a good leaving group such as a tosyl group, just like the one we see right here. The tosylates can then undergo an SN2 substitution to obtain an alkyl halide. So it will be a two-step process. No? Primary and secondary alcohols can also be converted to alkyl halides using PBr3. Now, the mechanism for the PBr3, we see it right here. You get the attack here, right? We have a bad leaving group. This pair of electrons is going to be attacking the phosphorus. And then you form this complex, right? This adduct, right? Which is when both things sort of come together. And now this big thing right here is actually a better leaving group than the OH by itself. Now you have a good leaving group lined up. Now all you need is that halogen to come in. In this case, it's going to be bromine. Bromine, the one that actually left in this first step, is going to come back and do that attack via SN2. So one step, you get the backside attack, you get the leaving group leaves, you get the corresponding alkyl halide. Just like in the previous example, we have the same challenge with the alcohol, that the hydroxyl group is a poor leaving group, doesn't really participate in substitution reactions very well. Thionate chloride, or SOCl2, solves that problem by converting the alcohol into a much better leaving group, just like we saw before with the PBr3. The alcohol oxygen first attacks the sulfur and the SOCl2, forming an intermediate. After a few proton transfers and elimination steps, we create a chlorosulfide group, which is an excellent leaving group. Chloride then performs an SN2 attack, displacing that group and producing the alkyl chloride. The important result is that that chloride thionate group converts an alcohol into an alkyl chloride, and because the final step is SN2, the stereochemistry is inverted at the carbon where the substitution occurs. Now, a few chapters ago, we saw that alcohols can undergo elimination under acidic conditions. We saw that you can take the hydroxyl, turn it into a corresponding alkene. Tertiary alcohols follow SN1 mechanism under these conditions, just like the one we see right here. You have your bad leaving group, you protonate it, turn it into a good leaving group, you form your stable carbocation, and you deprotonate, and pair of electrons come back here, you have that terminal alkene. Now, let's remember that E1 elimination usually favors the more substituted alkene. So what that means is that in this case, you have this group is the one leaving right here, and when you get the carbocation, you have that deprotonation step. You can either form an alkene here, but you have the alpha and the carbon, and then one, or it can go either here or here. It's actually symmetric, so it can go either way. Out of this carbon right here, or either of these are the ones that are going to be more substituted, so I would expect this guy to be my major product and then my minor. And the less substituted alkene would only be favored if we had an E2 elimination using a strong bulky base. If the alcohol is converted into a better leaving group, then a strong base can be used to promote E2 elimination, just like the one we see here. E2 reactions generally prefer over E1 reactions. In this case, E2 pathway is not really susceptible to rearrangement, and redox selectivity can actually be controlled. You can choose between Zaitsev and Hoffman product. So for now, we've seen that alcohols can be formed by reduction of the carbonyl, like we saw that throughout a big chunk of this chapter. Since we talk about reduction, you can't really talk about one without talking about its counterpart, which is the oxidation. So when you go from the carbonyl to the alcohol, we're talking about reduction, but when you go vice versa, from the hydroxyl to the carbonyl, you have what we call an oxidation process. Oxidation of primary alcohols proceeds to an aldehyde, and later on, if you keep oxidizing, it proceeds to a carboxylic acid. Oxidation of secondary alcohols will produce ketones. It stops there, doesn't really produce esters or anything like that. Tertiary alcohols generally don't really undergo oxidation because they don't really have any protons at the alpha position, so right here. Because it can't participate, then we say that there's no reaction there. There are many oxidizing agents that can be used to oxidize an alcohol. Some of the more common oxidizing agents are chromic acid. It can be in either form in aqueous acid. We also have potassium permanganate. It's actually very common as well. And we have others, but this is the one that we're going to be talking about first. Chromium trioxide and sodium dichromate in aqueous solution, in acidic condition really. You form your chromic acid. And then from there, you proceed to oxidize your reagent, whatever that is. Oxidation of the alcohol with chromic acid involves two steps. First, the formation of a chromate ester, and second, the elimination to form the pi bond. So first step, we have the alcohol interacting with the chromic acid, and you have the chromate ester right here. This is a fast process. This is a very reactive species, but it's also irreversible, so there's a low energy barrier involved in this process. And once you are at the chromate ester step, then you proceed to an elimination E2 type reaction, so one single step, to form the corresponding ketone in this case. Chromic acid will oxidize a primary alcohol to a carboxylic acid, so it goes all the way. PCC, or pyridinium chlorochromate, can be used as the oxidant to produce an aldehyde. So this is what PCC looks like. These are fairly large molecules, that's why we tend to use shorthand notations or abbreviations when writing down the reactions. Regardless of which of the oxidants you're going to be using, either chromic acid or PCC, if you have a secondary alcohol, you will turn it into the corresponding ketone. One of the major drawbacks of these reactions is that chromium tends to be very toxic and really bad for the environment. So we work toward developing alternatives that are more environmentally friendly, some of which we're going to be covering here. The first one involves what we call the Severn oxidation. It involves the use of DMSO and oxalic chloride to form what we call the active oxidant, which is this guy right here, chlorodimethyl sulfonium ion. Once we have that, then we proceed for the chlorodimethyl sulfonium ion lead oxidation. It is attacked by the alcohol, and a triethylamine facilitates the elimination to form the pi bond, just like what we see here. Through this process, secondary alcohols are oxidized to ketones. Just like with PCC, the Severn oxidation converts primary alcohols to aldehydes, the corresponding aldehyde, whatever that is. Another alternative is the Demartine periodine oxidation, which yields analogs of the Severn oxidation. So this is the Demartine periodinane. That's pretty much it. DMP oxidation is believed to proceed to a periodinane intermediate. Now we say it's believed because these tend to be very short-lived, and it's very difficult to figure out exactly the structure of that intermediate. We do know the products, and we are very good at predicting and figuring out and obtaining actually things that the products that we set out to obtain. DMP oxidation is non-acidic and doesn't really require high temperature, but chromium oxidations do. So in terms of industry, DMP is actually much more attractive because high temperatures mean that high energy and means high costs, right? So if you can avoid that, then that's actually more cost effective for you. Now let's talk a little bit about redox reactions in terms of biologicals. Nature uses reduction oxidation, quite a lot actually. They tend to be generally complex and selective. One of the compounds that we like to examine is NADH, which is a reducing agent. We have this entire structure right here. This being the reactive center. Everything else is sort of structural. The reactive site of NADH acts as a hydrate delivery agent, just like sodium borohydrate, lithium aluminum hydrate, but less violent. This is one way in which nature converts carbonyls into alcohols. So you have the NADH, the active site, you have the hydrate, it attacks, and then you get the electron transfer here. The carbonyl will grab a proton, and as a consequence, you get your two protons, one from your reducing agent, one from your solvent, and you get your alcohol. The NADH-NAD+ intercurvature plays a key role in metabolism. You will see a lot of this when you look at biochemistry. Now let's talk a little bit about oxidation of phenol. Recall that tertiary alcohols do not undergo oxidation because they lack an alpha proton. Alpha proton is a proton in the alpha carbon. You might expect a phenol to be similarly unreactive. In reality, phenol is actually easier to oxidize than primary or secondary alcohols. Phenols oxidize to form benzoquinone, which in turn can be reduced to hydroquinone. Quinones interconvert with hydroquinones, which is a key process in cellular respiration. So this is actually something that nature prefers quite a bit. And what about the chromium though? So typically, reactions will fall into two categories when we talk about synthesis strategies. First, changing the carbon skeleton or changing the functional group. Some of the reactions we've seen so far, going from an alkyne to an alkene to an alkane, we've seen that plenty throughout the semester. Now we have reactions that interconvert primary alcohols with aldehydes and secondary alcohols with ketones. With that in mind, we actually have a number of reactions that we can actually carry out, number of steps. There are some examples. My advice is for you to familiarize yourself with this schematic that we have here, where all the reactions are interconnected with one another. Recalling that Grignard reaction is a carbon-carbon bond forming reaction, so you can actually add carbon atoms to your skeleton. It's actually very convenient for us. Adding this to our little stockpile of reactions is actually very convenient. So for us, there is no one reaction that converts an aldehyde into a ketone, but with a Grignard reaction followed by an oxidation, we can actually accomplish it in two steps or two reactions. First, with our Grignard reaction, we take the carbonyl, turn it into the alcohol. We can then oxidize, and as you can see, the proton, we added the R with the Grignard, and as you can see, we took the aldehyde and we turned it into the ketone. That's actually very convenient. So we can summarize that by writing it like this. That's pretty much it.